Hey guys, welcome to the video tutorial designed to help you with your upcoming torque test. Now, it's not just going to be over torque, obviously. You've got some angular momentum, some rotational conservation of energy type problems, conservation of angular momentum, but you've also got some rolling without slipping type stuff. So what I want to do first is kind of go over most of the formulas that you will need tomorrow, and then start doing some examples that will benefit you for tomorrow's test. So what I want to talk about first is rolling without slipping. Now, any problem that states this in either the prompt or in your answer, some formulas need to come to mind. And so probably the two most important formulas are the relationship between your linear velocity and your angular velocity. So all you do is you take your angular velocity and you multiply it by your radius, and that gives you your tangential velocity, or think of it as, you know, if you're rolling like this, you've got, a lot of them are like a bowling ball or something, and you've got a radius, and they want to know the velocity that a particle would experience at the very edge, outermost edge, something like that. And then the tangential acceleration is going to be the same relationship, but it's going to be alpha r, your angular acceleration. Now, these two formulas are also important, but also remember the comparable kinematic equations. So an example would be like omega final squared equals omega initial squared plus 2 alpha d theta, something like that. So the comparable angular equations that are similar to our kinematic equation. Okay, so next we moved into torque, and we developed several formulas that talked about torque, and so the most basic one we had was FL, L being your lever arm. We then got here, which was RF sine theta. Again, the point of this being to get the perpendicular component of my force, or we just said that R was F tan. This is useful if you've got a wheel system. You know, you've got a radius and then you've got a mass hanging off. You know that your tangential force is this mass's weight, so you can use that to calculate your torque. And we said that the sum of my torques was equal to my moment of inertia times my angular acceleration. Now, moment of inertia, we said, was the summation of my masses times my radius. So, this is useful finding torque, because then if you know the moment of inertia, then you can calculate the acceleration, which will lead you to your angular velocity, so on and so forth. And so, next we moved into kind of kinetic energy. And we said that the kinetic energy due to rotation is 1/2 I omega squared. And this led us into problems where, you know, you had a incline. That looks terrible. You had an incline, and you had a ball with initial speed and an initial angular velocity. And how far could it roll up? Well, you know that you have kinetic energy due to your translational velocity, and now we have this extra term, which is kinetic energy due to our rotational velocity, and you would set that equal to your change of potential energy, which would just be mgh, and then you'd want to know what your height or how high it could roll, or problems like that. Those are the varying types of problems that you would see with a problem like that. So this led us into definitions of work, And so work we defined initially as the change in kinetic energy. And we also said that work was the integral of my torque d theta from your initial angle to your final angle, or we said that work was equal to the integral of my moment of inertia times my angular velocity. And this led us into power. Power being your change in work over your change in time, in which we also said could be my torque times my angular velocity. Now, I will tell you that this definition of power will be very useful on your multiple choice. Just FYI. Now, after we did conservation of kinetic energy, this led us into angular momentum. And so we said that angular momentum L was the cross product of my position vector times my momentum, which we said was R cross with mv. And we said that we could calculate the magnitude of my angular momentum as mvr sine of theta, specifically to get us mv. In a sense, it's my lever arm, but it's the perpendicular position component. And our last definition of angular momentum we said was I omega. Now, another useful definition that we got out of this was torque was my change in angular momentum over my change in time, specifically the net torque. And so if the sum of my torques was equal to 0, then I have no change in angular momentum, which means I have a constant angular momentum. Now, this led us into the conservation of momentum, which said that our initial need to equal our final. So in other words, our initial moment of inertia and angular velocity needs to equal our final moment of inertia times angular velocity. And so this led us to the type of question that's on every single test. We did an example of it with Einstein when he was holding the dumbbells, and he was holding them out at some initial speed, and then he drew his arms in. And so what had to happen there is, since he drew his arms in, he decreased his final moment of inertia, which meant that his angular velocity had to increase. Now, what happens here is that when he draws his arms in, his angular momentum is conserved, but his kinetic energy is not conserved. In fact, his kinetic energy would increase. Okay? So, when you're dealing with that type of situation, your angular momentum is conserved, but your kinetic energy due to rotation increases. Okay? So, that's kind of the gist of most of the formulas that you need. Again, I don't want to give them all to you because then that would be just too easy, wouldn't it? So, let's do an example. Let's say that I've got a cylinder and it is spinning, and let's say it's spinning around this axis going right through, and it's spinning with some angular velocity omega. Now, let's say this is like the, I can't remember what the name of the ride was at Frontier City. It was the Twister, I think, or something. But let's say I've got a box or a mass M that's suspended on the side of this cylinder so that it's not sliding up or down. And let's say that I want to know what the coefficient of friction needs to be in order to satisfy this situation. Well, I'm going to use this right here, but I need to break it up into my vertical and horizontal components. So if I think about my horizontal forces, well, the only force that I have horizontally is my normal force. Well, that equals my mass times my radial acceleration. Now, we already know from our circular motion portion that a rad is v squared over r. Now, from what we defined earlier, that our velocity is going to be equal to omega times my radius, and then that squared over r. And so what I can do is relate my radial acceleration, in other words my centripetal acceleration, to my angular velocity. So my radial acceleration in this case is just going to be omega squared r. And so my normal force is equal to just that, my mass times my omega squared times my radius. Now, let's look at the forces in the vertical direction. Well, I know that it's not going to slide up or down, so the sum of my forces needs to equal 0. Well, my forces in the vertical direction are going to be my frictional force. Okay? Specifically, let's go ahead and just call that Fs. Minus my weight needs to be equal to 0. In other words, my static frictional force needs to equal my weight. Now, friction, if we remember the equation for friction, it's my mu times my normal force. And so what I can do is replace this friction component with mu times my normal force, which I got earlier as m times my omega squared, this is mass, not to be confused with mu, times my radius. That equals mg. And so what I can do is I can cancel the m's on both sides, leaving me with my mu needs to be equal to, or it could be greater than. Could be either one, but it needs to be at least g over omega squared times r. And so this is how we can relate our, in a sense, this thing is rolling and it's not slipping. And so we can relate our radial acceleration to our angular velocity using the relationship that v equals omega r. It's a very useful relationship when dealing with those types of problems. And so let's look at another example. And let's say that I've got a wheel. Hang on just a second, let me get rid of this. Let's say that I've got a wheel and it's got a moment of inertia that is equal to 4m r squared. And it's got a radius r. And its angular speed, let's just say that it has an angular speed of omega. And let's say that it's increased from 0 to this final speed. And let's say it's done this over a time period t. So delta t, let's just say that equals t. And let's say I want to know the net torque. So I want to know what my torque is. Well, a useful relationship here is that we know that torque is equal to my change in angular momentum over my change in time. Well, my angular momentum, we said, was I omega. And so what this would become would be, if it's increased, let's say my initial angular speed is 0. This would be my L final minus my L initial over my delta t, which is just t. So that would become my moment of inertia, which would be 4m r squared times my final speed, final angular velocity, over t. Right there would give me my net torque. So do not forget this relationship along with this relationship. coupled together, they're very useful for solving these types of problems. Now, if I wanted to know, say I wanted to know the power now. Power is my change in work over my change in time. And so, if we think about work being the change in kinetic energy, and so what I can do is I can say that my work is equal to the change in kinetic energy, and my kinetic energy is equal to 1/2 I omega squared. So I could utilize this relationship and solve for power. Just in case you had to do something like that on your test. Now, let's look at one more example. Let's say that, what do I want to do? Let's look at a conservation of rotational energy, or conservation of energy type problem. And let's say that I've got a ball. Let's say I've got a ball. And it's going to roll up this incline, but I don't know what the height is going to be. And so it is rolling with an angular velocity, and it also has a translational speed, I'll just call v. And let's just say that its moment of inertia is, let's just say it's mr squared. It's a special ball. And it's got a radius r. And I want to know what is the max height that this ball can roll to. Well, what I'm going to have to do is I'm going to have to utilize the conservation of energy and say that my kinetic energy due to translational motion plus the kinetic energy of rotational motion, and then plus my potential energy initially needs to equal my final kinetic energy and my final potential energy. Well, if it's going to roll to a stop, then I know that I don't have any final kinetic energy, and I'll say that I also don't have any initial potential energy. So this is just going to equal mg times some height h. Now, kinetic energy due to translational is just going to be 1/2 mv squared plus 1/2 I times my omega squared equals mgh. Now, I'm going to replace I with mr squared. 1/2, and here we've got mr squared. Now, I'm also going to replace my angular velocity. I'm going to get everything in terms of my linear velocity. And so we know that v equals omega r. So what I do is I solve for omega, so I get v over r. So I plug that in, and so I get v squared over r squared. Oh, look how beautiful that worked out. Equals mgh. So I cancel my radii, and I'm going to go ahead and cancel my masses too. And so that gives me 1/2 v squared plus 1/2 v squared equal to gh. So that gives me v squared over g equal to my height. So those are the type of problems that you can expect. And again, there are some more problems that you can expect that I obviously haven't gone over. Just remember your training and look over your notes and also the free responses that I gave you. Also look at the lab that you had where you had a two-wheel type system, and you had a mass acting on this one and a mass acting on that one. That'll be very helpful for your test. So good luck, and I will see you all tomorrow or today.